In today's video, we are going to discuss about various new column designs or the modification in the existing column design so as to save energy if the column is not properly placed, or even if the column is not properly placed and we try to change the pressure, like either increase or decrease. But by doing that, if you want to either take the column above pinch or below pinch, but that also is not practically feasible because of one or other reasons, as discussed in the previous video, where we have seen that increasing pressure has its own impact, decreasing pressure has its own impact, apart from just changing the temperatures of condenser and reboilers. So in that case, we are left with few options for designing column in a different way. Naturally, these all options would require one to invest some amount of money, at least moderate to higher amount of money, when you want to go with the or suggest with the new column design. So there are a few options available with us. We can use intermediate reboiler or condenser. We will discuss as we proceed further. When we use reboiler, intermediate reboiler or condenser, we may modify the design in order to save energy. We may come up with a new design completely for maybe a sequence, and we may come up with heat pumping for the given distillation column. Let us see them one by one. So if I am having, say for example, a column which is not properly placed, then can we save an energy by placing an intermediate condenser or reboiler? So naturally, when we put an intermediate reboiler or condenser, that will be put up at a temperature level which is different from the actual condenser and reboiler. So for condenser, if I talk of intermediate condenser is available to me at a higher temperature than the actual condenser, and intermediate reboiler is available to me at a lower temperature than the actual reboiler. This will make the use of energy which is available with the process either above pinch or below pinch. So let us try and see that. So this is a typical intermediate condenser, and if I look here in figure B, it has been shown that the column is not properly placed. We see that the energy is received from the process above pitch, and it is given back to the process below pitch. Now, if I have some intermediate condenser, and as I told you, intermediate condenser will have a temperature greater than the actual condenser. So this is your actual condenser and this is your intermediate condenser. So what we can do is by putting up an intermediate condenser, we can exchange the heat equivalent to intermediate condenser. So we can take the heat from the process which is equivalent to intermediate condenser, and then we can give it back. So the energy balance here is not getting impacted, and hence we can save some amount of energy from the utility section. So my requirement would be QH minimum plus Q reboiler minus intermediate condenser for the hot utility, and for condenser as well, what we have is QC minimum plus Q condenser, but this Q condenser will be the actual condenser duty minus Q intermediate. So we can save some amount of energy if we place condenser intermediately. The similar thing we can discuss if the column is not properly placed, but then if we put a reboiler. Now if I go back, like if the column is properly placed, right, but there is an issue with the heat load. So the heat load associated with the column is more than what a process can supply with, right? In such case also we can use intermediate condenser. So if we see that, let us look at the column C, where we can see that column is very properly placed with respect to the process. Reboiler is also above pinch, condenser is also above pinch, but the heat loads within Q reboiler and Q condenser are such that we cannot supply the entire amount of energy from the process to the distillation column. In such case also, we can have an intermediate condenser, and there will be an exchange of energy which is equivalent to Q intermediate only, and thereby your energy balance within the process will always remain in such a way that your pinch point is not shifted and there is no negative heat flow within the process intermediate temperatures scales. So we can use intermediate condenser in order to save some amount of energy when either the column is not properly placed as has been shown in figure B, or even if the column is properly placed but the heat loads are not sufficient within the process, you can use this to save some amount of energy. Naturally, the addition of one heat exchanger should be evaluated against the amount of energy which we are saving. The next is maybe making changes in the, like this also is very similar, which we'll talk about the placement of your distillation column. If the energy is not sufficiently available, this is where you can put an intermediate condenser, otherwise the condenser will require energy here. So this also is a very classical example of using of intermediate condenser in order to save some amount of energy from the process. Another aspect is splitting the column loads. So what we do is that rather than having one column, right, we bifurcate our feed into two columns. So this is your feed is splitted. So when the feed is splitted, right, the feed is splitted for, let's say, 50-50. So the load on column 1 is 50% of actual and load on column 2 is 50% of the actual. Now what we do is, since the actual column is not appropriately placed, we change the pressure of the bifurcated column. So C1, which is 50% of actual, and C2, which is almost 50% of the actual, we decrease the pressure in such a way that reboiler and condenser both temperatures are below pinch, and we increase the pressure for column 2 in such a way that both reboiler and condenser are above pinch. So correspondingly, the TH diagram, if I see, you can just see that C2 pressure has increased, so the entire column is moved upward. This is your pinch point, and the column 1 has gone downward. So this way we can make the split of the total load, and then we can integrate column 2 above pinch, column 1 below pinch. Naturally, we need to take again care about the changes in pressure which are taking place, with how does it impact the design of the column. But basically a single column gets converted into design of two separate columns. One thing which we have to keep in mind is that uh, that in this case, see, we are splitting the feed itself. So both the columns will have the same distillate and same bottoms. So it's not that we are designing two separate columns. The column will perform at the same requirement. The feed to the columns would also be the same. We just change the mass which is going to the column, and secondly the pressure, right? And thereby we try to save some energy. So this is something which will happen if I draw it on a TQ diagram. Another aspect is splitting tower operation. Now this is a bit different from what we have seen in earlier case. It is very similar, but the amount of saving in energy is taking place in a completely different form. Here what is happening is that we split the tower into two. So if I look at the diagram which is on the next slide, I split the feed into two. Now I increase the pressure in such a way of one of the columns and decrease the pressure of the second column in such a way that I can exchange energy between the reboiler of one column and condenser of column 2. So what happens is that I'll change the pressure here in such a way. So this pressure will be high and this pressure will be low. Now what happens is, when I decrease the pressure, naturally the boiling point will decrease. So I'll decrease the pressure in such a way that the boiling point here of this species is less than the boiling point of this condensing liquid or condensing vapor, I'm sorry. So what will happen is that the condensing vapor, that the vapor needs to be condensed, will be able to give away the energy to the liquid which needs to be reboiled. So naturally this temperature here, T2 if I say, of condenser has to be more than T1 reboiler. So the change in pressure of column 1 and 2 will take place in such a way that column 1 reboiler temperature will be less than column 2 condenser temperature, and thereby I can exchange the energy between column 2 condenser and column 1 reboiler. What is the benefit of it? The benefit here is that I need to supply here the energy, right? This energy is reused here by passing on this energy from this vapor to this liquid. So the energy is used twice, and then here I'll be using utility. So this is cold utility and this is hot utility. If I compare it with only single column, so in single column I'll require hot utility 1 and cold utility 2. So this will be much more than UH and UC, right? So we split the load, hence the total amount of energy required would be less, but then the same energy is reutilized. So that is what has been discussed here, that feed is splitted into two and then sent to two towers operating at a different pressure. Pressures are adjusted in such a way that the condenser from high pressure can provide heat to the reboiler of lower pressure. Feed split needs to be adjusted to have equal duties of boiling and condensation. That will make sure that you save energy of almost equivalent amount. The energy required will be almost half the original required. So if there are two columns, you can split the requirement, you can reduce the requirement into almost half. If I add the third column here on top with another pressure, wherein this condenser and this reboiler can exchange energy, then what will happen? I supply heat here, it is reutilized one, it is reutilized second time, and then I have third condenser duty. So my requirement would go 1/3. Likewise, if theoretically I can put up n towers, my requirement of the energy will go to 1 by n. However, practically that's not feasible because very simple reason. As you increase the number of columns, so all the accessories required would change, and another aspect is, as you keep on changing the adding the column, your pressure requirement will also be different, and you'll have to keep on increasing or decreasing the pressure as you add the columns. So practically we have two towers, and that's why this is called as a double effect. Double effect is same energy is utilized twice. The temperature difference across the system will naturally increase. Condenser of low pressure tower may require refrigeration, and reboiler of high pressure may have fouling problems. So these are the limitations associated with this particular scheme. Third, another aspect which we can do is a thermally coupled distillation column. This is generally like this we can do when you have column in sequence. Now if you look at the left hand side conventional arrangement, what we have is we have got two reboilers and two condensers, and the columns are operating without any exchange of energy. What happens on the right hand side is that we feed ABC to column 1, and column 1 design would change slightly, in fact majorly, and what will happen is that a side fraction will be taken out, will be sent to column number 2, and it will exchange energy with the contents of column 2, and then partially it will come back. So this will, column 2 will work as a kind of an intermediate energy exchange equipment, and thereby it will also exchange the mass. So it will be like, it will be energy and mass both will be exchanged, so the mass transfer will also take place, and because of that what will happen is that the B rich component, B rich solution will go to column 2, where the B will be vaporized, it will go towards the distillate, and the C rich solution will come back to column 1, and it will be condensed and concentrated, it will be concentrated, and it will go towards the bottom of the column, and it will be coming out as a product C. So what we are saving is we'll be able to save the energy, and we will also have the design modification, and we'll have a separation of ABC. So this is termed as thermally coupled distillation column, which will save energy, right? But this is generally we can take place when there is a sequence of column. So we discussed about three different things: intermediate reboiler, modifying the design, and thermally coupled design. And when we meet next time, we'll talk about heat pumping. Heat pumping is nothing but reutilizing the energy, right, from top or from bottom. So when we meet in our next video, we'll discuss about how do we save energy by heat pumping, which is also known as vapor recompression or reboiler flushing. Thank you.